Hello everyone, I am Karthik, Assistant Professor of Mathematics, SNS College of Engineering. In this lecture video, I will explain about limits, continuous, analytic functions of complex variables. Okay, what is limit in a complex analysis? In complex analysis and in real analysis, limits are used to describe the behavior of functions as their inputs approach a certain point. For a complex function f of z, where z equal to x plus iy, as z approaches a complex number a equal to x naught plus y naught I, we say f of z tends to limit L if for every positive number epsilon there exists a positive number delta such that 0 less than z minus a less than delta, then modulus of f of z minus L less than epsilon. This is definition of limits in real analysis. Continuous functions. A complex function f of z is continuous at a point z equal to a if the limit of f of z as z approaches a exists and is equal to f of a. Analytic function. A complex function f of z is said to be an analytic in a domain if it is differentiable at every point within the domain. Complex numbers. Complex numbers are that can be expressed in the form of a plus ib, where a and b are real numbers and I is imaginary unit defined as I square equal to minus 1. Complex plane. Complex plane is a geometric representation of a complex numbers where each complex number is associated with a unique point in two-dimensional plane. It is often called the Argand plane or Argand diagram, named after the mathematician Jean Robert Argand. Real axis. The horizontal axis represents the real part of the complex numbers. It analogs to the x-axis in the Cartesian coordinate system used in real numbers. Imaginary axis. The vertical axis represents the imaginary part of the complex numbers. It's perpendicular to the real axis and is analogs to the y-axis in the Cartesian coordinate system. Polar form of complex numbers. The polar form of the complex number provides an alternative way to represent complex numbers using their magnitude and argument. It is particularly useful for performing operations like multiplication, division, and exponentiation of a complex number. The polar form of complex number z is given by z equal to r into cos theta plus I sin theta, where r is the magnitude or modulus of a complex number, r equal to modulus z equal to square root of a square plus b square. Theta is the argument or angle of the complex number. Operations with complex numbers. Operations with a complex number such as addition, subtraction, multiplication, division, and exponentiation. Addition and subtraction. To add or subtract complex numbers, you simplify, combine their real parts and imaginary parts separately. Addition. For example, a plus ba plus c plus di equal to a plus c plus b plus d into I. Similarly, subtraction as well. Multiplication. To multiply complex numbers, you can use distributive property and the fact that I square equal to minus 1. In multiplication, a plus ba into c plus da equal to ac minus bd plus ad plus bc into I. Division. In division, a plus ba divided by c plus da equal to ac plus bd plus bc minus ad into I divided by c square plus d square. Exponentiation. To raise a complex number to a power, you can use de Moivre's theorem which states that cos theta plus I sin theta whole power n equal to cos n theta plus I sin n theta. Limit and continuity of a complex function. In complex analysis, the concepts of limits and continuity for a complex functions are analogs to those in real analysis, with some important differences due to the presence of two dimensions. Here, how these concepts are defined in for the complex functions. First one is limits of the complex function. Just like in real analysis, the limit of a complex function as the input approaches a certain complex number z0 is defined in terms of neighborhoods around z0. Continuity of a complex function. A complex function f of z is said to be an analytic at a point z equal to z0 if limit z tends to z0 f of z exists and is equal to f of z0. Differentiation of a complex function. The differentiation of a complex function is a fundamental concept in complex analysis, analogs to differentiation of real functions in calculus. There are some unique aspects to consider due to the presence of two dimensions in complex numbers. Uh, Given a function f of z where z equal to x plus iy and f of z is u of x comma y plus I into v of x comma y, the complex derivative of f of z with respect to z denotes f dash z or df divided by dz. Cauchy-Riemann conditions. The Cauchy-Riemann conditions are a set of necessary conditions for a complex function to be differentiable at a point. They are named after the mathematician Louis Cauchy and Riemann, who made significant contributions to complex analysis. Let f of z equal to u of x comma y plus I into v of x comma y be a complex function defined in the neighborhood of a point z equal to x plus iy, where u of x comma y and v of x comma y are the real and imaginary parts of f of z respectively. First condition is dou u by dou x equal to dou v by dou y, that is differentiation of u with respect to x equal to differentiation of v with respect to y. Second condition is dou u by dou y equal to minus dou v by dou x. Differentiation of u with respect to y is equivalent to negative of v with respect to x. Applications of complex variable. Complex variables find applications in various fields due to their versatility and analytical power. In physics, uh, we use complex in electromagnetism and quantum mechanics. In engineering, we mostly used in control theory and signal processing. In mathematical analysis, we use complex analysis and conformal mapping. In mechanical engineering, we use vibrations and waves. In aeronautics and aerospace engineering, we use complex number in aerodynamics. In finance and economics, we use complex numbers in option pricing. In fluid dynamics, we use potential flow. These are the some applications of complex variables. Sorry. Thank you.